Right. So I think last couple of lectures, we covered object detection, we covered semantic segmentation, we also covered instance segmentation. Now, next couple of lectures, we are moving away from images and we are going to look into videos, how we can extract meaningful features or meaningful representation from those videos. Okay, so the first topic we'll cover is optical flow, and it is I think very primitive kind of features which you can extract from videos, and it's used for a lot of problems, a lot of applications, and this is sometimes also this can replace, like, if you extract your normal features from your videos or RGB videos. So you can also replace optical flow with those kind of features. So it works pretty well. So today we'll see like a couple of approaches how we can extract optical flow from a video. And I think next lecture I'm going to cover action detection, how you perform action detection in videos. And we will also look into like what are the different kind of problems they like. We have action recognition, we have detection, and what are the problems we try to solve in videos. And we'll give a brief overview how we can solve all those problems. And then we will have one more lecture after that. In that, we will try to cover camera modeling. That's like classical computer vision. And then I think we will have a break for Thanksgiving. So we won't have class, I think, on 26th or 27th. And on first or second, I think one of the lecture, you're going to have your second midterm. Okay, so let's begin. Here, we are just seeing an optical illusion. So what's happening here is if you look at these two images and you try to hold your you try to hold your eyes, don't move your eyes or don't blink, then you won't see any motion, right? But as soon as you are blinking your eyes or you are moving your eyes, then you will see that you are seeing some kind of motion in both of these images, right? So it's an optical illusion, and the reason why it's happening is, so these are like rabbits here, black and white, and you can see that there's high contrast between where these rabbits are placed. So if you look at this white rabbit on the left, you can see it's like the background is black, and so it's high contrast. On the right, it's yellow, so it's not that contrastive. And similarly, if you look at the black rabbit, it's contrasted like at both ends. And one thing you will observe is that depending upon how these rabbits are arranged or how these the contrasted backgrounds are arranged, you will see that some of these patterns are moving clockwise and some of these are moving counterclockwise. And that's just like the difference in how these colors are arranged. So for example, this one, your contrast is like towards the clockwise side, right? But in this one, it's on the opposite side. So even though you don't have any motion here, but still you are seeing some kind of motion, right? So, and this is not just true for humans. There was like a nice video from YouTube where the same illusion was shown to a cat, and you can see that she's also experiencing the same thing. So, which is kind of interesting. Okay. So as I said, like the patterns will only move when you blink or move your eyes. If you don't move or don't blink, they will be static, because in reality there is no motion. These are just images. And again, how the rabbits are arranged, how the contrast is like changing in the pattern, that will define like in which direction those patterns are moving. So let's see like why we need to estimate visual motion. So first of all, let's try to understand what visual motion is. So the images I showed, that was just optical illusion, but it was kind of giving you an idea, an intuition, why you experience motion. Okay, so when you're looking at a video, motion can occur due to camera instability. If you're moving your camera a lot, so your pixels will change, right? You might have some kind of jitter as well in your pixels. Or the other is like the other scenario is where when in fact like there is some kind of motion happening, you have some kind of dynamics. So that can be due to moving objects, and it could be like if you're moving your camera in one direction or the other, again then all of the pixels in the scene are going to move. Okay, so visual motion tells you a lot about the spatial layout of the scene you're looking at. So if you have a motion parallax, so this is like this can be used to determine the depth of your objects. All right. So what will happen is if you try to close one of your eye and then try to move, then you will see that the objects which are closer to your eye, they will like you will see a lot of motion for those objects as compared to the objects which are far in the background. And if you again try to capture the same thing by closing the other eye, then if you try to like merge these two together, that will tell you if the motion is large, that object is closer to your eye. So it's kind of depth estimation for you. So that's just one simple application where you can use this kind of motion. Now we can capture motion in terms of optical flow. Okay, so whenever we are trying to estimate visual motion, that can be determined using this flow information. And there are different methods to extract optical flow from the videos. The classical ways is patch based. So you don't look at the full image or the full video. You only look at smaller patches. And there are these two famous methods, which one is like Lucas Canade and the other is Horn Schunk. So we'll go through the first one and briefly cover what this tries to do. And then recently we have all these neural network based approaches where you don't have to design like that algorithm. You just use a CNN or a convolutional neural network, feed in the input, and that network will predict the optical flow for you. So there is one, I think one of the first neural network designed in, I think 2015, this is called FlowNet. And of course, there are like many derivatives of this. Many papers have tried to extend this method to improve it. So we'll briefly cover how we can extract optical flow from a video using this FlowNet architecture. Okay, so there are many different applications of optical flow. For example, if you have a video and you want to perform some kind of segmentation in that video based on motion. So what you want to do is, given a video, if you see some motion in any of the region, you want to segment that out. So that's called motion-based segmentation. You can use optical flow for that. Another good example is structure from motion. So this is like you will have just a video which is showing you a sequence of 2D projection of your 3D world. And structure for motion, what it does is it tries to reconstruct the 3D scene or the 3D environment. Okay. Then this alignment is another interesting application where what you have, let's say you have videos captured from UAVs, which are like unmanned aerial vehicles. So you want to align like the videos captured from UAVs and videos captured from the ground. Then this is, I think, a very popular, very well used application of optical flow, which is video compression. So I think all of you might know about MPEG and AV, all the codecs you have for videos. So what they try to do is they try to reduce the size of your videos. And there are a lot of optimizations, and optical flow is one of them which is used. And the idea here is, if you have a video, if you try to save each and every frame in that video, then the size of the video will be huge, right? So then what we do is we try to compress that. We try to get rid of redundant information. And the idea is, if you are moving from one frame to another, there might be pixels in those two consecutive frames which are not changing. So if the pixel values are not changing, then you don't need to save the second frame, right? And you only need to save those pixel locations where there is some kind of motion, because those values are changing. And your videos are usually 30 frames per second. So for each second, you have 30 frames. So if it's like an hour-long video and you try to save all those frames, it's going to be huge. So then optical flow can play a vital role there, because optical flow will tell you if objects or pixels in your videos are changing or not. And then you can use that to do some kind of compression. And there are different techniques to do that. It can be also used for object tracking. So for example, if you have a video and there is an object, let's say a car, and the car is moving, and what you want to do is you want to track that car across all the frames in the video. And one simple technique could be like you have seen object detection. So you perform object detection on all the frames and then track just that detection. But you can also make use of optical flow, because optical flow will tell you where each of those pixel locations is moving as you move into like subsequent frames in the video. And then that information can be used for tracking. And this is just another application, deformation analysis, how your the shape or the appearance of the objects are actually deforming or changing or varying across frames. So optical flow will also help you in that. So those were like different kind of applications, but this is really interesting. And what we are seeing here is that, so how the animals move, then that information actually is very crucial for diagnosing these neurological conditions or many other applications in this neuroscience. Now, what people used to do is they used to watch the captured frames in the videos and then make analysis, which was not that trivial. It's very tiresome, right? You have to watch all those videos. Now, computer vision can play a big role there, because if you have higher speed cameras, like which can capture these motions at a very high rate, then instead of humans watching those videos, you can use computer vision tools to analyze each of those frames, how the motion is evolving. And optical flow can play a very vital role there to analyze like how the patterns are changing, or how the motion of these animals is evolving. So this is again like a very unique kind of application of optical flow. So let's try to understand how we can actually extract this optical flow from videos. Before that, let's try to understand what do we mean by motion. Okay, so if you look at this image on the left, right? So we can perceive that this person may be like running towards left, and depending upon how we are observing this image or this video, or how it was captured using the camera, the motion in this input image or this input video will be different. For example, let's consider the first scenario where your camera was just looking at the center and you're not moving your camera. Okay, then what will happen is this person will start from this location, and probably if he's running in this direction, after some time, he will be at this location. Okay, so the motion is, if you try to interpret that, the motion will be from this direction to this direction, and it will be for the pixels which belong to this person. Okay, only those pixels are going to change the position. But if you change the way how you're observing that motion, so another scene, again, same person running towards left, but this time what you're trying to do is, instead of just looking at the center of the frame or the center of the video, what you will do is you will try to follow this person as he's running. So then if this is your camera, then if the person is here, you're looking at this direction. If a person is here, you're looking at this direction. So you're kind of rotating your viewpoint from left to right, all right? So it's kind of, you're just focusing on the actor or the running person. Then if you try to understand like what kind of video you will get. So in this case, if the camera is directly focusing on this person, then the location is not going to change, because every time the every time the camera is just looking onto the person directly. And in this case, what will happen is all the pixels in the background, they will kind of move towards the right. So in this case, you can see that optical flow or the motion is towards the left, and the motion is for this pixel. But in this particular scenario, the motion is of the background, and all of the background is moving towards the right. So these arrows are representing that motion. Okay, so it depends upon how you're observing the scene or the action. Based or depending upon that, you will have different interpretation of this optical flow. So far we have seen just images, and videos are nothing but they are a sequence of images, and these sequences are like evolving over time. So images, we have just we had a function which can be represented as a function of x and y, just two variables. But videos is we have a extra dimension which is called time. So each pixel value in a video you can represent as a function of x, y, which is like the spatial location and a time step t. Okay, so it's like instead of a 2-dimension, it's moving in a 3-dimension. And let's see like how motion can be represented. So if these are 3 consecutive frames of a video, right? And you have an object, let's say this orange dot over here. And this dot, let's say in the first image was at this location, in the second image at this location, and in the next at this location. So if you look at individual frames, then it's hard to interpret what's happening. But if you combine all these 3, then you can say that this circle here or this dot here, it's kind of moving from left to right. And you can represent that using like this, just one moving dot in this frame. And the reason you can do that is because all of the background pixels are not changing. Only this object location is changing. So it's easy for you to say that, okay, the object is moving from this point to this point. Okay. Now, a simple way to describe motion could be, you can just take a difference of different pixel values, right? So for every pixel, what you can do is take 2 consecutive frames and just subtract the value. And what it will give you is if the intensity, let's say you're just taking grayscale images. So if there is a change in intensity, it means there is some motion, right? And if the intensity is not changing, it means the position didn't change. So if you try to look at these 2 frames, and these frames are like from a video where a person is walking from left to right, and you can see that the background is really static here. So none of the pixels are changing. Now, what you do is for each pixel, you just subtract the intensity to the previous frame. And if there is no change, you will get a black value, right? A black pixel value. And if there is a change, it will be like very high value. So it will be close to 255, and you will get a white pixel. So you can see that all the pixels which are like on top of this person are getting very high value. So this is kind of giving you a rough estimate of motion from these 2 frames. Okay, so that's like a very simple way, the way you can extract your, or you can describe your motion. Now, optical flow, it's like the idea here is you want to estimate how your objects are moving from one frame to another. And an easy way to define that is using a vector field. Okay, so it's a vector field of a displacement. And what we do is we try to find out, like for each point, we try to find out in the next frame, how much did it move? So how much did it move like in the X direction, how much it moved in the Y direction. So for each pixel location, we will have an optical flow, which will give us 2 values, and we call that optical flow vector, okay, or just call it optical flow. So let's try to understand that using a sample, a couple of sample images. So this is an image at time step t. Okay, and this is again an image of the same scene at time step t plus dt. So you can see here that all these objects are static. They're not changing their locations. But if you focus on this particular toy here, so it moved from this location to this location as you move from time step t to dt. Okay. So the intensity at this location from this image, it will be a function of x, y, and t. Okay, and the intensity of, again, the same pixel after moving to this location, it will be x plus dx, y plus dy, and t plus dt. So this is dx is how much this object or this pixel location moved in the x direction, and this dy is how much it moved in the y direction, and dt is just like how far away these frames were with respect to time. Okay, so this dt. Now, if this pixel location moved from here to here, then we can assume that the intensity is not going to change. And again, that's an assumption. It might not be true. So if we have that assumption, then we can say that the intensity at x, y, t should be equal to intensity of this new location, which is represented by these three additional parameters. All right. So this is like a basic equation which is used to find optical flow. And now your optical flow will be this change, how much this location changed in the x direction, and how much it changed in the y direction. And this is like dt, just like the time span you are looking at for that change. So these three variables define your optical flow. Okay, so this is again showing the same thing, your pixel at this location xy. Okay, and again the new location, this is x plus u, y plus u. And here you can see that you are just ignoring your change in time, you're just adding one. So you can ignore that, right? And then u and v are the displacement vectors, which also refers to your optical flow. So one big assumption here is that we are assuming that given an object as it is moving, the intensity or the brightness, whatever you're using like to compute the optical flow, it's not changing. And again, it's a very harsh assumption, because in a video, I mean, you might know that if object is moving, of course, like its shape or different, there's certain features, certain appearance features which will not change. But if you just focus on the intensity value, it might change because it depends on a lot of conditions, right? The illumination, like how much lighting you have, and that's definitely going to change. So that's why we call this like a constraint which you're using when we compute optical flow using this method. So if we have that constraint, we can easily say that the intensity at this location will be equal to intensity at this location. This is the same equation which we saw in the previous slide. Now, if you take the Taylor expansion of this, the function on the right-hand side. Okay, so what you can do is, if you try to ignore the higher order terms, then this will be reduced to, so yeah, that's the function. So it will be equivalent to x, y, and t. Okay, so that's the first term from the Taylor series, and these are the next two consecutive terms, and you will be ignoring all the higher order terms. Okay, and later we will see that how that's also an issue if you ignore those terms. And if you ignore, then you can see that this is the equation you will get. Here, if you will look at this, so this is Ix, and this Ix is nothing but it's just image derivative along x direction. And again, this Iy is the image derivative along y direction, and this It is the derivative along the time dimension, the third dimension in the video. Okay, so if you just try to simplify this, you can bring it on the left-hand side, and you know that from this constancy equation, because of this constraint, these two will be equal. So you can cancel these two. Okay, so your equation will be this term equals to 0 or equivalent to 0. And this is called your optical flow equation. And in almost all the methods in the classical computer vision, this is the equation which is used to figure out like or to estimate the optical flow in a video. Now you can also represent this equation in a matrix format. Right, so U, V are your vectors. So displacement in x direction, displacement in y direction with respect to time. And then this is like, you can arrange these image derivatives in form of matrix. So you can represent that as this delta of image, right? And this IT is just in the intensity as intensity at time t. So that's like just another representation. Now this is another representation of the same equation. So that was the equation we got. This is called brightness constancy constraint. And this is in fact the compact form. But the original form, you can see that if you compute the image derivative in x direction, it can be represented as this partial derivative of image along x. And this u is your displacement vector in the x direction. And displacement is with respect to time. And that will be equivalent to your derivative of x with respect to t. And we earlier saw that if we change this change in time to just 1, then this can be just like the displacement. Okay, and similarly, like for y as well, this is partial derivative of the image along y direction, and this is just a derivative of y in t direction. And this is again your partial derivative of image along time. So these two equations, they are equivalent, and this is like the optical flow equation. Now, if you look at this equation carefully, so given an image, computing the partial derivative along x, that's fine, you can do that. Again, you can compute this, and you can also compute this. But what is unknown here is the displacement vector in x direction and displacement vector in y direction. And that's exactly what you need to compute the optical flow. But the issue is you only have one equation and you have two variables. Now, from your courses, like I think linear algebra or numerical computation, you might have learned that if you have two different variables, then you need exactly two different equations to solve that problem, right? So therefore, this is like kind of underrepresentation, right? Because given just one equation, you cannot determine like two different unknown variables. And the issue will be, we can go into detail, but briefly, just to give you a brief idea. So you have two variables here, right? And you know that if you have an equation in two variables that represents a line in 2D plane. So let's say your optical flow equation is represented by this line, and this is the normal. Now, if you put like any values of u and v in that equation, which amounts to 0, which gives you 0, right? Then what will happen is that a uv point will be in that line. And that's how you get 0, right? Now, if you try to move along that line, then also that point will lie in the same line, right? It means you have multiple solutions to that equation. And that's the reason you cannot exactly determine what will be the value of u and v, because they are infinite solutions. So let's see how we can fix that. Okay, so that was our constraint number 1, the brightness constraint, where we assume that the intensity of any object or any pixel location will not change as we move along time. And we will need like another constraint where we can determine u and v so that we have more equations to solve those two unknown parameters. Okay, so before going to that, let's try to figure out like what are the other issues in computing optical flow. So the first issue is aperture problem. So in this case, you can see that if you have these two lines and they are kind of moving in this direction, but what you're doing is you're not actually observing the full view. Your aperture is pretty small. You are looking only at this region. Now, when the lines will move in this direction, then what will happen is if you only look through this aperture, you will perceive the motion in this direction. All right. So let me try to make that more clear. So in this case, you have two square patches. All right. So the background, it's fixed. And let's say this particular shape is moving in this direction. So what will happen is the gap between these 2 points will reduce. And you can also assume that, let's say, it's the same block. So the first position is this and the second position is this. So both are fine. Then the motion is in this direction. All right. Now, if your aperture is at this particular location, then it will be very easy for you to figure out that, okay, this point is moving from this location to this location. And that's the true motion. But let's say you are looking from a different aperture and you are looking at this location. Then what will happen is these points over this line, all of these points will move towards left. And I think the motion which you will get is just towards moving all the pixels moving towards left. And if there is some intensity difference between the pixels which are on the border, then it may happen that you are able to get maybe somewhat like a northwest motion. But again, getting this motion will be very difficult by looking at this location. So that's called aperture problem. And I think I have another example which will make it easy. This is called Barber pole illusion. So if you look at this motion, then you can easily say that things are moving downwards, right, from top to bottom. There is no doubt in that. Now, if I show you the full picture, if I increase the aperture, then if this is the motion, and in this case, you can see that it's the same motion, but in this case, all your pixels are actually not moving from bottom to top, but they're moving from right to left. Okay, so again, it's a very different example to explain that aperture problem. So depending upon what portion of the motion you are looking at, your optical flow will be different. Okay, now coming back to the issue of solving two variables using one equation. So to do that, what we can do is we can try to introduce more equations and introduce one more constraint, which is called spatial coherence. And the spatial coherence constraint, it was proposed in 81 by these authors, Lucas and Kennedy. And this is a very famous method to compute optical flow. And I think you will find many different implementations of this method. So what they proposed is, they proposed that we should have a spatial coherency in the neighborhood of each pixel location. Okay, so they say that in a small neighborhood, what will happen is all the pixel locations will have same optical flow. Okay, so this UV represent your optical flow. So in a neighborhood, all these will be similar. Then what you can do is, let's say your neighborhood is 5 cross 5, and I think the best window was found to be, I think, 3 cross 3, but it's fine. You can take any window. So if you take 5 cross 5 window, and then in that window, you are saying that all the pixels will have same optical flow, which means that you can get 25 different equations for those two variables, U and V. All right. So then these are the 25 different equations. So the first equation from one pixel, second from second pixel, third from third pixel, and all those equations will share these U and V, the optical flow parameters, because they are saying that optical flow will not change in this small neighborhood. Now, you just needed two equations, but this way you have 25 different equations. And this is kind of your, we call this over-parameterized. And you can solve these 25 equations to get the value of those two. And there are different ways. So we'll just go through one of that, which is called least square solution. So you have these 25 equations, you can stack them in form of a matrix, right? Because you have this partial derivative of x, partial of y. Similarly, you will have for all the 25 different points. And you represent this matrix as A, and D is your displacement vector, the optical flow, which will have two different variables, U and V. So this is shape 25 cross 2. This is shape 2 cross 1. And B is your partial derivative across time. So you will be having 25 different values here. So it's 25 cross 1. Now, from linear algebra, you know that to solve such equation, what you can do is you can simply take inverse of A, and if you multiply with A inverse, then this will be one identity matrix. And here you will get A inverse B. And then you can easily solve that to get these values of U and V. But in this case, the issue is the matrix is not square. And if a matrix is not square, you cannot get an inverse of that matrix. So to solve such a system, the easy trick is you make this matrix square. And to do that, what you can do is you can multiply this matrix with A transpose. So A transpose is just you are shuffling the rows with columns. And the shape of this matrix, A transpose, will be 2 by 25, right? And when you multiply a matrix of 2 by 25 with 25 by 2, you will get a matrix which will have a shape 2 by 2. And that's a square matrix. And then you can easily invert that square matrix and then solve this equation. So that's called least square solution. And so that's the equation after you multiply it with A transpose. Okay, you can do the math, it's pretty trivial. So then you can, this is a square matrix, A transpose A, you can easily invert this and find the value of U and V. And that's also called pseudo inverse. Okay. Now that was one representation how you can solve this. Let me walk you through another way to solve that equation. And here what you can do is, so this will be your energy equation, right? The same equation, what you do is you try to do the integral and then this should be 0, right? Now for a small neighborhood, what you want is you want this equation to be 0 for all the locations in this small neighborhood, right? So you take the squares and then you integrate, and this sum or this energy function should be close to 0. So this xy, this integral is over a small neighborhood. Now, what we want to do is we want to minimize that, right? Because we want this equation to be close to 0. This is our optical flow equation. So you know from your calculus that if you want to minimize a function, you can just take the derivative and make it 0. All right. So what you can do is you can take the derivative of this equation and make it 0. So since this is in two variable, you will have to take partial derivatives first with respect to u, then with respect to v. And the derivative will be simply like, so this is this times 2 will be over here, then the same term. And when you take partial derivative with respect to u, all of these will be 0, but you will get ix from here. So that's the ix. And when you take a partial derivative with respect to v, again 2 times the same term, the first term here. So this will be 0, this will be 0, but here you have iy, so you get iy. So you get these two equations. All right. Now again, you can, if you try to solve, you can bring this in and you will get something like the equation which you got in the previous slide. And again, you can represent that in the matrix format. And in this case, what's happening is your matrix is already squared matrix. So you can easily take an inverse of that and solve for U and V. Okay, so that's kind of solution which you will get. Now, that's the Lucas-Kennedy method to compute optical flow. Now you can see that to compute the optical flow, what you need is you just need partial derivatives of the image in the x direction, partial derivative in the y direction, right? And then you can just use these equations to get the values for U and V. So all of this is like coming down to computing partial derivative. So now you can see that how powerful that idea of taking image derivative is. You started from edge detection. Again, these partial derivatives were the way to go. Then I think the next step was detecting the key points. Again, there as well, you saw that how these derivatives are useful. Then again, when you move to extracting features from the images, so use, let's say, histogram of orients, right? Or even SIFT descriptors. There also what you need is image derivatives. So you will see like in all the classical computer vision approaches, image derivative is something which is very important. Now, that was the simple equations to get the displacement vectors for Lucas Canary. And one thing you can see is that we have one parameter, and that parameter is like what should be the neighborhood, right? This neighborhood we should use for computing the optical flow. And depending upon this window, you will get different result. Okay, that's what we are trying to analyze here. So this is the first image, this is the second image, and this is showing like three different results using different window size. This is a window size of 3, so window size of 5, window size of 11. Okay, so almost all I think you can see that you have the motion in this direction, which is the right motion. The plane is moving in this direction. All right, and you can see that in the borders, there are some errors, right? So there's a reason for that, and I think we will briefly cover that as well. So the issue in the borders is that the matrix T, it becomes singular, and it's very hard to compute the right optical flow in these border regions, and that's like one big limitation of this Lucas Canary algorithm. Okay. Now we started with this one constraint, which was called brightness constancy, and most of the times you will see that if you have realistic video or realistic images, this constraint will not hold, and that's the reason like you will not get very high quality optical flow when you use this method. So that's limitation number one. Then another big limitation is the spatial constraint, right? Where we assume that all the pixels in the neighborhood they will have the same optical flow, and it might not be true for all the cases. And that's why we have regularization based methods, and that's the next method I think we will cover briefly. The other issue is the motion may not be very small, like from frame to frame. Like sometimes there might be very fast motion. A pixel might move very far away from its current location. And in that case, what will happen is your assumption that your higher order terms in Taylor series can be ignored, which will not hold because they will also include like some useful information which you need for that equation. Okay, so that's the reason if you have very high motion in your videos, then this Lucas Canary method does not perform pretty well. Now that can be actually addressed. So what we do is, and again this is coming back from your feature extraction, right, and even edge detection. What you can do is you can build pyramid of your image derivatives, and then what will happen is if you have a very high motion, in the small resolution, that high motion will be converted to a very small motion. So what's happening here is in this image pyramid or this pyramid of image derivative, you have the same motion in different speeds because of changing the resolution of the image. So again, you can see that how powerful this Gaussian pyramid or this image pyramid idea is. You saw this for feature extraction. This is useful for edge detection. You also saw that this was useful for object detection, right? And now you're looking into optical flow, and it's playing a role here as well. Okay, so that's how you try to fix the issue of very high motion in your videos and still capture that. Okay, so again, this is another sample showing results from Lucas Canary. So this is a tree, and what it's trying to show here is that if you have a very high motion, which is happening like in the borders here, so it will fail, right? And there are two reasons. The first reason is there will be very high motion, and the second reason will be these are just borders, so the derivative will change very drastically. Okay. Now, if you use image pyramids, then you can see that how this optical flow has changed from that pretty bad prediction to very good prediction. All right. So you can see that the foreground of this tree trunk, it's pretty stable. And again, you're just seeing these motion in the boundaries. Okay, so then the other issue where we were assuming that all the pixels in the neighborhood, they might not have the same kind of optical flow. So there is another method, this is called Horn and Shrunk. And so they added one more constraint. So they call that, so they try to minimize this global energy again. So this term we already had in our first method. But in addition to this, they also have this smoothness constraint. So they are saying that the optical flow in the neighborhood, it should be very smooth. It should not change very much, right? So by adding this smoothness constraint, they show that how the results can be improved. So anyways, we are not going to discuss this in detail. So that was just the intuition. But again, when you can just solve this equation and get the values for a u and v, it's just you have extra term here. Okay. So again, to solve this, you have to minimize this. You can take partial derivatives, equate them to 0, and you will get your solution. Now, those were like classical methods. Now, this is like deep learning era, and people have proposed like a lot of deep learning based methods which can be used to predict optical flow. And FlowNet was, I think, among the one of the first method which tries to do that. So what they do is they take the pair of images, and they have a CNN architecture which predicts the optical flow, and they have the ground truth optical flow, and they can use that to compute the loss and then train the system. And at the end, this network will be trained. Given any two images, you can predict the optical flow. Okay. So you can see that no equations, no theorems, no proof, just have the network, train it, and you will get the results. Now they have two different variants. So the first variant was a simple network. And here what they did is they take the images. So they are working on 384 by 512. So that's the resolution of the image. And here you can see that the number of channels we have is 6. So what they did is they just concat those two images. So 3 channels from the first image, 3 channels from the second image. And then they use a standard CNN network, right? Just convolution, max pooling, convolution, max pooling. And they get this latent representation here, which has a shape of 6 × 8, 1024. And you can see that the resolution is pretty small as compared to this. And similar to autoencoder, and also like the problem when you were looking into image segmentation or semantic segmentation, we need to upscale this to the original size, or maybe like at a higher resolution to get a good estimate. So for that, they have this refinement network. We will go through this, what this refinement network is. And these are the skip connections coming from the earlier layers, giving you fine level details of these features. And this is similar to what you used to do for U-Net architecture, right? For semantic segmentation. We discussed that in the last lecture. So this was one variant, a very simple architecture. The second variant was, so they argued that the network might not be able to learn the correlation between these two images when we just perform convolution. So then what they did is they use separate heads to extract features from these images, right? So then these two separate images, just 3 channels here, conv layers, conv layers, conv layers. And once they have extracted the features, then what we can do is we can try to find correlation between patches between these feature maps. And that correlation, the idea is that correlation will give you what kind of displacement is happening when we move from this image to this image. And this correlation, again, is the same equation we have seen before when we were trying to do image filtering, right? It's the same equation, but the difference is we are doing correlation between these activation maps. So we'll take patches from this activation map, then patch from this activation map, find the correlation. So that will give you some value. And we do that for like all the possible locations. And the another variant was we look at a small neighborhood when we find the correlation. So it would not be like the same locations in this feature maps. So we take one location in this feature map, and then we will search in the neighborhood of that location in this feature map and find correlation for all of those. Okay, so that's the simple equation. So you know this is a correlation. And this is the neighborhood which we will use, like the kernel shape for finding the correlation. And there is another parameter, I think, which is called D. That's like the neighborhood in which you will search to find the correlation. So for each pixel location, if you are looking at a D square, different locations, your output will be, the shape will be shape of this, and then you will have these D square times different channels. So this is 441. It means that they were looking at 21 different locations. Okay. And so this first block of feature map, it's coming from that correlation, but you can see here that you have another feature map here, which is coming directly from the conv operation on these features. All right. And then the rest of the network is same as the previous network. And again, the refinement network is also similar. You have these skip connections which are going into the refinement network. So now let's look at what this refinement network looks like. So these are the features coming into the refinement network. They used deconvolution operation, all right? And these are the features coming from the skip connections from the encoder network, these, okay? So for each of these layers, you have these skip connections. So you concat the features and again perform deconvolution, again concat. So keep doing that, you break the optical flow. So another variant they had is, it's not a variant, I mean, they have that in the refinement network, but the trick is what you can do is you can use these features to predict the optical flow at a smaller resolution. And if you look back into the previous slides where we were looking into that fully convolutional network for semantic segmentation, it was trying to do exactly the same thing. It was trying to predict the output at different resolution, right? So this will be very coarse level, and as you move on, it will be very fine grained level, and eventually we'll have very high resolution result. One big difference is when you make the prediction, you will have a loss term here as well. Then what they did is they use this predicted optical flow and concatenated it with the features as well here. So to upsample the features or learn these features, they were also making use of the predicted optical flow at a coarse level. And that actually helps in learning better features for this optical flow prediction. So that was the simple refinement network, nothing new. It's like all we have seen before. And of course, when you can train such a network using a loss function, if you have the ground truth optical flow, you can just compute pixel-wise loss. You can use either cross entropy loss. You can also compute mean squared loss, and then just train the same way you train your classifiers. Now, these are some of the results from for some of the images. So another interesting thing here, we can see that how you represent your optical flow. Okay, so this is the center, and we're trying to color code the optical flow. So if the pixel is not changing at all, we will pick the color from the center. Okay, so all the locations where you can see that it's close to white, it means there is no motion at all. And the color you will pick, if this pixel moves from this location to this location, then you're going to pick this color. And again, if the pixel is moving in this direction, you will pick this color. And again, how much the displacement is, you can see that the gradient of this color is changing. So if the motion is pretty high in this direction, you're going to pick this dark blue color. And here, this dark green. So the idea here is whenever you see dark shades of these colors, which means there is a high motion, and this color coding will tell you in which direction that motion is. So that's a pretty nice idea to do to visualize this optical flow. And so these are the ground truths, and these are some of the methods. This is FlowNet S and C. So the simple one, the first one, and this is using correlation. Okay. So you can see that how this is actually improving after including the correlation. Now let's briefly, what's the time? Okay, we have time. So briefly talk about some of the applications. So as we discussed earlier, this can be used for target tracking. Let's say we want to track this person here. Then what we can do is we can compute the optical flow. Then we know that where this person moved in the next frame. So we can just use that optical flow to do the tracking. Uh, Optical flow, it's very useful in performing action recognition, and we will talk about this in the next lecture, how we can actually combine optical flow and features extracted from RGB frames of the video, and then how that improves the action recognition performance. Okay, so this is useful for action recognition, and you can also use this for motion modeling. So you can see that this is just showing two consecutive frames of a video and how the car is moving. And this is the estimated optical flow. So what you can do is you can take the first frame and apply this optical flow on that first frame, and that's called warping. So you will change the pixel locations based on this optical flow, and that will give you the second frame. And this idea is pretty useful when you have to do maybe image synthesis, or you have to do video prediction. You want to predict future frames. So then this kind of technique is pretty useful. You can also use optical flow for motion segmentation. So in this case, you can see that this car is moving. So if you find the optical flow, you can separate that region from the background, which is not moving. And that will only give you like the foreground motion of this frame. Okay, so this is called motion segmentation. This was another, I think, interesting application. And let me see if I can play this. Okay, so I think the video was not embedded properly here. And the idea here was, if you have two consecutive frames, or let's say you have sequence of frames, and you compute the or estimate the optical flow, that can be used to also estimate the human pose. So human pose is like the skeleton. So you have these joints in the arm, right? And so all these joints you can estimate using just that optical flow. So I don't have that demo. I don't know what was the issue. So yeah, that was all. So these are some further readings if you are interested in this problem. This is from the book from Zelensky, chapter 7, and these are some of the papers. And again, if you want some like implementation, you can find at these links. You can play around with that. All right, so any questions?